The void is endless, a canvas of black velvet pierced by pinpricks of light that have traveled eons to reach us. Imagine standing on a spacecraft, your breath fogging a viewport as you drift farther from home than any human has ever been. Out here, the sun, the heart of our world, the golden beacon that has warmed our faces and lit our days since time immemorial, is no longer a blazing orb. It's shrinking, fading, becoming just another star in a sea of countless others. This is the story of Voyager 1, humanity's farthest flung messenger, and the question that haunts me: when does the sun, our anchor in the cosmos, become indistinguishable from any other star? How far must we go before our home star loses its majesty? And what does that mean for us, for Voyager, for our place in the universe? Voyager 1, launched in 1977, is a relic of human ambition, a time capsule carrying our hopes, our music, our voices into the infinite. As I speak, it's 166 astronomical units from the sun, 166 times the distance from Earth to our star, and it's speeding away at 3.5 astronomical units per year. That's a number so vast it's hard to grasp, like trying to hold the ocean in your hands. Out there, the sun isn't setting because of a planet's spin. It's fading because Voyager is plunging deeper into the cosmic night, racing toward a darkness where our star's brilliance dims. I couldn't shake the thought: what does the sun look like from that far away? How faint can it get before it's just another speck in the sky? So I did the math, and the numbers told a story that sent chills down my spine. At 166 astronomical units, the sun's brightness, its apparent magnitude, is negative 5.7. That's a number astronomers use to measure how bright something appears in the sky, and to put it in perspective, it's still 3 magnitudes brighter than a full moon on a clear night. Imagine standing under a full moon, its silver glow casting shadows so sharp you can read by them. At 166 astronomical units, the sun is 16 times brighter than that. It's not a disk anymore, not a radiant sphere you can't bear to look at. It's a point of light, but one so fierce it still drowns out all but the brightest stars. Picture yourself out there, floating beside Voyager, your eyes locked on that distant sun. It's still the king of the sky, washing out the fainter stars like a spotlight in a darkened theater. But it's not invincible. The farther you go, the more its dominance wanes. I used a tool called Space Engine to simulate this view, locking the exposure to mimic staring at the sun from Earth, then pulling back to Voyager's distance. The result was humbling. The sun, even at 166 astronomical units, is a beacon, but it's no longer the untouchable god of light it once was. It's bright enough to make you squint, but the stars around it are starting to hold their own. This got me thinking: how far would you need to go for the sun to fade to the brightness of a full moon? The math is straightforward but profound. The sun's apparent magnitude from Earth is a blinding minus 26.83. A full moon, under perfect conditions, is minus 2.74. The difference between them is 14.09 magnitudes. And there's a formula for this, a way to translate brightness into distance. It tells us you'd need to travel 658 astronomical units, 4 times farther than Voyager is now, for the sun to dim to the brightness of a full moon. At that distance, the human eye would still see clearly, but you'd be so far from home that the sun's warmth would be a distant memory, your body shivering in the cosmic cold. 658 astronomical units. It's a distance that feels like a betrayal of everything familiar. To put it in perspective, a comet on a parabolic orbit, one of those celestial wanderers that grace our skies, would take about 1,000 years to reach that far. No comet we've ever tracked with certainty has ventured that deep into the dark. There are ancient comets, ghosts from humanity's past, that might have drifted out there after swinging by the inner solar system, but none in living memory have reached a place where the sun is just one of the brightest stars. This is the edge of our understanding, a frontier where the sun's grip weakens, and the universe begins to feel indifferent. I couldn't stop there. How far would you need to go for the sun to look like Mercury, the third brightest natural object in our sky, with a magnitude of negative 4.2? The answer staggered me. 30,000 astronomical units, or 194 light days, half a light year. At that distance, the sun is no longer the unrivaled lord of the sky. It's a bright star, yes, but it's starting to blend in, outshone by the likes of Sirius, the brightest star we see from Earth at negative 1.46. To make the sun fainter than Sirius, you'd need to push out to 118,000 astronomical units, nearly 2 light years. 2 light years. That's when our sun, the center of our world, becomes just another twinkle in the night. This journey into the abyss isn't just about numbers, it's about what those numbers mean for us. Imagine Voyager, that tiny probe, carrying a golden record etched with humanity's dreams, drifting through a sky where the sun is no longer special. It's a lonely thought, but it's also humbling, a reminder of how small we are in the grand tapestry of the cosmos. And yet, Voyager keeps going, powered by a fading nuclear heart, sending whispers back to us across the void. I found myself wondering about other stars, other skies. There's a star called Gliese 710, about 1 light year from another called Nu Serpentis. In Nu Serpentis's sky, Gliese 710 shines at a magnitude of negative 5.5. Brighter than our sun appears from Voyager's current perch. And here's something wild. In about 1.3 million years, Gliese 710 is projected to pass within a quarter of a light year of our sun. Future humans, or whatever we become, might look up and see it as a brilliant new star, slowly drifting across the sky. But its passage could stir the Oort cloud, sending comets raining down on the inner solar system a million years later, a cosmic ripple from a fleeting visitor. These calculations, these glimpses into the far future, are built on a system that's both ancient and ingenious, the magnitude scale. It's a way to measure brightness that stretches back over 2,000 years, to a Greek astronomer named Hipparchus, who gazed at the stars and tried to make sense of their light. He didn't have telescopes or computers, just his eyes and a relentless curiosity. He cataloged 850 stars, noting their positions and their brilliance, calling them bright lights of the second degree, or faint. A couple of centuries later, Ptolemy refined this, assigning numbers, first magnitude for the brightest, second for the next, down to sixth for the faintest visible to the naked eye. It was a system born from human perception, from watching stars emerge in the twilight and noting which ones appeared first. That's where this story pauses, on the edge of ancient wisdom and modern exploration. With Voyager carrying our dreams into a sky where the sun is just a star, and the universe whispers secrets we're only beginning to understand. The stars are storytellers, each one a chapter in a book older than time itself. As Voyager 1 drifts farther into the cosmic sea, it carries us with it, not just in metal and circuits, but in spirit, in the questions we hurl into the void. How did we, creatures of a small blue world, come to measure the brightness of stars? Why do we care so deeply about the fading light of our sun, seen from a probe that's been traveling since before many of us were born? The answer lies in a thread that stretches back to ancient nights, when humans first looked up and tried to make sense of the heavens. It's a story of curiosity, of trial and error, of people like you and me who refuse to let the universe remain a mystery. As we follow Voyager's journey, we're also tracing the path of an idea, one that began with a Greek stargazer and grew into the tools that let us calculate when our sun becomes just another star. This is the heart of our tale, where human ingenuity meets the infinite, and where the past and future collide in a dance of light and wonder. 2,000 years ago, a man named Hipparchus stood under a Mediterranean sky, his eyes scanning the constellations. He didn't have a telescope or a computer, just a mind burning with questions and a heart that ached to understand. He cataloged 850 stars, scribbling their positions and their brightness, calling them brilliant lights of the second degree, or faint. It was a rough sketch of the cosmos, drawn by someone who saw the stars as more than just lights. They were a puzzle, a challenge. A couple of centuries later, Ptolemy picked up the thread, giving numbers to this system. First magnitude for the brightest stars, second for the next, down to sixth for those barely visible in the twilight. It was a way of seeing the universe through human eyes, born from watching stars emerge as the sky darkened, noting which ones flickered into view first. Imagine Ptolemy, standing on a hill, his breath catching as a star winked into existence, its light a whisper from across the ages. That simple act, watching, naming, measuring, laid the foundation for everything we know about the stars today, including the calculations that tell us how far Voyager must travel to see the sun fade. But the story didn't stop with the ancients. As centuries passed, the heavens grew deeper, more complex. The invention of the telescope changed everything. Suddenly, astronomers could peer into the dark and see stars too faint for the naked eye, like secrets the universe had been hiding. But with this new power came a problem. The human eye, for all its wonder, isn't great at judging brightness. You can tell one star is brighter than another if they're side by side. But through a telescope's narrow field of view, that comparison gets tricky. Astronomers struggled to extend Ptolemy's system to these fainter stars, and for hundreds of years, they fumbled through the dark, trying to make sense of it all. By the early 19th century, they started crafting tools to tame the chaos. They used smoked glass to dim bright stars, trying to standardize what they saw. Then came Carl von Steinheil, a man with a clever idea, a telescope with a split lens, letting you compare two stars at once, like holding a conversation between lights in the sky. It was a step toward precision, but it still wasn't enough. The universe was too vast, too stubborn to be pinned down so easily. Then, in 1861, a man named Friedrich Zollner changed the game. He built a device called the Zollner photometer, a contraption that sounds like something out of a steampunk dream. It used a kerosene flame as a standard candle. Its light filtered through polarizing prisms to match the brightness of a star. Imagine Zollner, hunched over his photometer in the dead of night, tweaking prisms until the flame's glow matched a star's twinkle, then reading off the values like a poet deciphering the language of the cosmos. These devices were used well into the 1940s, even as photography began to take over, capturing starlight in ways the human eye never could. But there was a deeper problem. The magnitude system itself, that ancient scale from 1 to 6, was arbitrary, a relic of human perception. It worked for the brightest stars, but as telescopes revealed fainter and fainter objects, the system started to creak. How do you measure a star so dim it's barely there? How do you extend a scale built for the naked eye to a universe that keeps unfolding? The answer came from a man named Norman Pogson, an astronomer with a passion for asteroids and a knack for seeing patterns where others saw chaos. In 1856, he wrote a paper predicting the brightness of minor planets for the coming year, a paper that would have been forgotten if not for a footnote that changed astronomy forever. Pogson proposed a new way to define magnitudes, one that honored the human eye's logarithmic response to light. He suggested that a difference of 5 magnitudes should equal a factor of 100 in brightness. It was a simple, elegant idea, but it was revolutionary. If a star of magnitude 1 was 100 times brighter than a star of magnitude 6, the math became clean, using base 10 logarithms that made calculations a breeze. Other astronomers had tried different ratios. William Dawes used a factor of 4, but Pogson's number, 2.512, won out because it simplified the work. It was like finding the perfect key to a lock that had baffled scholars for centuries. Suddenly, astronomers could measure the brightness of anything, from the blazing sun to the faintest star, with a system that bridged the ancient and the modern. This magnitude system is why we can answer the question at the heart of Voyager's journey. How far must it go before the sun looks like any other star? The math is deceptively simple. A difference of 5 magnitudes means a star is 100 times brighter or fainter. And because brightness falls with the square of distance, 5 magnitudes also means 10 times farther or closer. From Earth, we see objects ranging from -30 to +30 magnitudes, a range of a trillion in brightness. It's a scale that captures the sun's blinding glory and the faintest galaxies we can glimpse with our biggest telescopes. But there's another layer to this. The difference between apparent magnitude, what we see from Earth, and absolute magnitude, what a star would look like if it were 10 parsecs, 32.6 light-years away. Our sun, for all its importance to us, is a cosmic wimp. At 10 parsecs, its absolute magnitude is 4.8. A fifth magnitude star most people would barely notice. Compare that to Rigel, a blue giant that burns at an absolute magnitude of negative 7.84, 1,000 light-years away. From Earth, Rigel's brightness is dimmed by distance, but if you brought it closer, it would outshine everything in our sky. Proxima Centauri, the closest star to us, is even fainter, with an absolute magnitude of 15.6, 10,000 times dimmer than the Sun. From a planet orbiting Alpha Centauri, Proxima would be a barely visible third magnitude star, a faint reminder of how distance reshapes the heavens. As Voyager drifts farther, it's not just leaving the Sun behind, it's carrying us into a future where our star becomes ordinary. At 30,000 astronomical units, half a light year, the Sun is as bright as Mercury in our sky. At 118,000 astronomical units, 2 light years, it's fainter than Sirius. But Voyager itself is running out of time. Its power supply, a radioisotope thermoelectric generator, is fading, and by the early 2030, it may go silent. Its instruments too weak to call home. Yet it will keep drifting, a silent ambassador, for tens of thousands of years. In 40,000 years, it will pass within 1.6 light-years of a star called AC plus 793888, and who knows what sky it will see then. The Sun will be a faint star, one among many, but Voyager's golden record will still carry our voices, our music, our hope. This is where our story pauses again, on the cusp of something vast and unknowable, where the light of our sun grows dim, but the light of human curiosity burns on. The universe doesn't care about our stories, but we tell them anyway, etching our dreams into the void. Voyager 1, that tiny speck of human hope, drifts ever farther, carrying a golden record that sings of Earth. Our laughter, our music, our longing. It's 166 astronomical units from the Sun now, racing at 3.5 AU per year into a darkness where our star's light fades. We've followed it to the edge, asking when the Sun, our life-giver, becomes just another star. The answer lies in numbers that feel like poetry. At 658 astronomical units, the Sun matches a full moon's glow. At 30,000 astronomical units, it's as bright as Mercury. At 118,000 astronomical units, 2 light-years out, it's fainter than Sirius, a mere twinkle in a crowded sky. But this journey isn't just about Voyager or the Sun, it's about us, about why we chase these questions, why we send fragile probes into the infinite to ask, where do we belong? Imagine standing on Voyager, peering back at the Sun, now a sharp point of light, no warmer than the stars around it. It's humbling, almost heartbreaking to see our star reduced to a stranger in the sky. Yet there's beauty in that loss, a reminder that the universe is vast, and we are small but daring. The magnitude system that lets us measure this fading light is a human triumph, born from Hipparchus's ancient gaze and refined by Pogson's elegant math. It tells us the Sun's absolute magnitude is 4.8 at 10 parsecs, a dim, fifth magnitude star. Unremarkable in the cosmic crowd. Compare that to Rigel, blazing at negative 7.84, or Proxima Centauri, a feeble 15.6, and you see how ordinary our Sun is in the grand scheme. From a planet in the Alpha Centauri system, our Sun would be a third magnitude speck, barely worth a glance. Yet to us, it's everything: home, warmth, life. Voyager's power is fading, its nuclear heart dimming. By the early 2030s, it may fall silent, no longer able to whisper back across the void. But it won't stop. In 40,000 years, it will drift within 1.6 light-years of AC plus 793888, a star we barely know. The Sun will be a faint dot in that alien sky, but Voyager's golden record will endure, a message to anyone or anything that finds it. And in 1.3 million years, when Gliese 710 grazes our solar system, stirring comets in the Oort cloud. Future beings might look up and marvel at a new star, unaware of the chaos it could bring. These are the timescales of the cosmos, vast and indifferent, yet they spark something in us, a hunger to explore, to understand, to leave a mark. This journey has shown us that the sun's light, so vital to us, is just one note in a symphony of stars. Voyager's path reminds us how fragile our place is, how fleeting our time. Yet it also shows our courage, our refusal to stay small. We built a probe to cross the heavens, to carry our voices where no one has gone. And though the sun will fade in Voyager's sky, it will never dim in our hearts. So let's keep looking up, keep asking questions, keep sending our dreams into the dark. Because even when the sun is just another star, we are still here, telling its story, reaching for the infinite.